Okay, so last time we were looking at this recurrence relation for the problem of counting the number of bits in an integer, and so we'll look at how to solve this. Let me make sure so now last time we did this factorial problem and we saw how to solve the reconciliation for that. Let me quickly go over that so that we can use the same approach for solving this reconciliation. So what we had in the factorial problem was this. So to find the factorial of n, by definition of factorial of n factorial is 1 times 2 times up to n. That means also 1 times 2 up to n minus 1 times n. And 1 times 2 up to n minus 1 is factorial of n minus 1 times this n. So that's a recurrence relation for finding factorial. So which means if you want to find factorial of n, you find factorial of n minus n and multiply that with n. So the multiplication is the basic operation here. So the number of times we do the multiplication is what we want to find. So m of n is the number of times we do the multiplication to find factorial of n. So according to this recurrence for factorial, so to find n factorial, we need to find n minus 1 factorial and do one more multiplication with n, that will get us n factorial. So the reconciliation for finding the number of multiplications can be accordingly written as if m of n is the number of multiplications to find f of n, m of n minus 1 is the number of multiplications to find f of n minus 1. So what will be the number of multiplications to compute n minus 1 factorial plus one more multiplication corresponding to this multiplication, we will get the number of multiplications for finding n factorial. Now this recurrence for factorial is true for n greater than or equal to 1, means it's also like equivalent to telling n greater than 0. So that's why I have written here for this number of multiplications, this recurrence is true for n greater than 0. Now 0 factorial is 1, so we do not really need any multiplication to compute 0 factorial. So the number of multiplications to compute 0 factorial is simply 0. So every reconciliation need to have both the basic condition like this, and this is really what the reconciliation is. A larger term written as a function of equal to the smaller term like this. Okay, so this is what we want to solve, and we took this approach of reducing to a lower order term and then coming up with a general recurrence relation and then solving it. So how did we do here is, so if m of n can be written as m of n minus 1 plus n for any n greater than 0, replace this n with n minus 1. So we'll get m of n minus 1 is instead of n minus 1. So n minus 1 minus 1 will be m of n minus 2 plus 1. So now instead of m minus 1, m of n minus 1, we can substitute this recurrence. That will lead us to m of n equals m of n minus 1 is m of n minus 2 plus 1. Then this plus 1 is here. So it is m of n minus 2 plus 1 is m of n minus 2 plus 2. Now again m of n minus 2 can be written according to this recurrence. Replace n with n minus 2. We're going to get n minus 2 minus 1, that is m of n minus 3 plus 1. So again replace in this recurrence m of n equals m of n minus 2 plus 2. For m of n minus 2 we can write m of n minus 3 plus 1 plus 2, and that's going to be m of n minus 3 plus 3. So you can see there's a trend here. If it is m of n equals m of n minus 1 plus 1, m of n can also be written as m of n minus 2 plus 2. So 2 and 2, and it's also equal to m of n minus 3 plus 3. It's 3 and 3. So in general, m of n can be written as m of n minus I plus I, where I ranges anywhere from 0 to n. Okay, so we need to now solve for I, so that you see here it reduces to lower order terms in the sense that n minus 1 is a lower order term compared to n. n minus 2 is a lower order term compared to n minus 3 is even further lower. So m of n minus I is lower than n. So we want to see how long we can keep on reducing to lower order terms. You can reduce something up to this basic condition. So we can go all the way to 0. So let us now solve for I by substituting n minus I equals 0, and that will n minus I equals 0 means I will be equal to m. So if when I equals n, this term will go to m of 0. So that's what we want to solve for I. So when I equals n, m of n equals m of n minus n plus n, and m of n minus n is m of 0, which is given as 0. So m of 0 plus n is 0 plus n is n. So what it means is the number of multiplications to compute n factorial is n multiplications, and n is theta of n. So this is how we could solve this reconciliation for finding n factorial of n. Okay. Any question on this before we proceed?
No.
Okay, good. Alright, so we then saw this problem finding the number of bits to represent an integer in binary. So again, in this problem we do not really look for the binary representation, but we want to count, just a count on the number of bits that we need to represent an integer in binary. And the integers we are dealing with is like greater than or equal to 1. So if you want to represent integer 1 which is in decimal in binary, we just need 1 bit, which is just 1. And for integers 2 and 3 in decimal, the number of bits needed is 2, because I think I wrote this last time, but let me write over it right again here. So for 1 in decimal, 1 in binary 2. For 2 in decimal, it is 1 0 in binary. For 3 it is 1 1. For 4 it is 1 1 0. For 5 it is 1 0 1. 6 is 1 1 0. So I made a mistake here. It is 1 0 0 for 4. Then 7 is 1 1 1. Then 8 is 1 0 0 0. 9 is 1 0 0 1, and you can go all the way to 15 is 1 1 1 1. Then 16 is 1 0 0 0. You can go all the way to 31, which will be 1 1 1 1. Then 32 is 1 0 0 0. You can go all the way to 63 as 1 1 1 1. So that's what I show here. For 2 and 3, we need 2 bits to represent them in binary. From 4 to 7, we need 3 bits to represent them in binary. From 8 to 15, we need 4 bits. Then 16 to 31, we need 5 bits. Then 32 to 63, we need 6 bits. So essentially then, as the range doubles, you see here there's only one integer in the range of just 1, and then 2 and 3 you have 2 integers. 4 to 7 you have 4 integers. 8 to 15 you have 8 integers. 16 to 31 you have 16 integers, and 32 to 63 you have 32. So as this range doubles, the number of bits you need to represent the integers in that range increases by 1, and that can be captured using this recurrence relation. The number of bits to represent an integer n in binary for any n greater than 1 can be written as the number of bits to represent half of that integer in binary plus 1 more bit. Now you have to have this, what is called this floor symbol, to take care of what I just said. The range just doubles, right? So let's pick one thing, say 8. So the number of bits represent 8 in binary according to the recurrence is n is 8, means n over 2 will be 4. So the number of bits represent 8 in binary is going to be same as the number of bits represent 8 over 2, 4 in binary plus 1 more bit. So the number of bits for 4 is 3 bits, then plus 1 more bit will give us 4 bits for 8. Now pick up the next integer in this range, which is 9. So the number of bits for 9 is going to be the number of bits for 9 over 2, and I'm taking a floor here, which means I'm just taking the integer part of this division. So 9 over 2 is 4.5 and I'm truncating it, so that means 4. So the number of bits for 4 plus one more bit, so the number of bits for 4 is 3 plus one more bit is 4 bits. So any two subsequent integers in this range, for 8 and 9, they're kind of being mapped to 4. Then 10 and 11 will be mapped to 5 in this range. So 10 divided by 2 is also 11, 10 divided by 2 is 5, 11 divided by 2 is also 5. Then 12 and 13, 12 divided by 2 is 6, 13 divided by 2 is also 6. 14 and 15 are mapped to 7. So two subsequent integers in this range are being mapped to one integer in the earlier range. That's why we have n over 2 with a floor symbol to justify that. So this is the number of bits, and this is one more addition because one more bit than the previous range. Now to represent integer 1, we don't need to follow this recurrence, because for integer 1, that's the basic condition. We know we just need 1 bit represent integer 1 in binary. So this is the recurrence for the number of bits we need to use, or we need to represent an integer n in binary. And we can write this as a pseudo code. If n equals 1, just return 1 is the number of bits we need. If n is greater than 1, because assuming you are passing an input n greater than or equal to 1. So if n is greater than 1, you can say it's the same as the number of bits represent n over 2 in binary plus one more bit. Okay. So for recurrence problems like this, it's very easy to come up with the code. So the key thing is to understand the idea behind this recurrence relation. Okay. So the basic operation here is the number of is addition, because we need like in the multiplication or factorial problem, the number of multiplications for finding n minus 1 factorial plus one more multiplication, right? So we repeatedly do multiplication here to find the factorial as n increases, whereas here we have to do plus one more bit. So this plus is the basic operation. So we can write a recurrence for the number of bits, number of additions that we need to find the number of bits represent n. So a of n is the number of additions we need to compute the number of bits for n. Same as the number of additions we need to compute the number of bits for n over 2 plus one more addition. That's why we have this plus one more addition. So this is plus one more bit, and that is one addition plus one more addition. So that's the number of additions, and this is for n greater than 1. Since the number of bits for representing integer 1 in binary is 1 bit, there's no addition involved here. That's a basic condition. An equivalent basic condition here is the number of additions we need to represent 1 in binary is 0, because we don't do any addition here. So this is the recurrence we need to solve. Okay. Now any question up to this point of coming up with the recurrence relation?
I have like a quick question about the calculation.
Yes.
Yeah. So, man, I can't see the slide anymore.
Let me. Do you want to go through this? One second. This thing. How I got the number of bits?
Yes, sir. I just wanted to take a look at that.
Okay.
Yeah, I was doing some calculation, and I had a question about like 8 bits being 8, like the number 8 being 4 bits, because if you divided 8 by 2, that gives you 4 plus 1, which should be 5 bits. I had a question about that.
No. Okay, I think you're mixing up the integer with binary. So what I have written on the left hand side is the decimal or integer, decimal representation, and then what I have written on the right hand side is the binary representation of those decimal values. Okay. So for decimal value 1, this is also the same binary representation of 1.
Yeah.
For 2, it is 1 0 in binary. Is that clear? 1 0 is 2. Then 3 is 1 1 in binary. Okay. Then 4 is 1 0 0. So let me write the exponents of 2 if that will help you to understand better. So the exponents of 2 are like what? 32, 16, 8, 4, 2, 1. So 4 is an integer in decimal, can be represented as, I think I explained this approach in some class earlier, either this course or previous course. So you go from the most significant the exponent to the least significant, but we want to represent just 4. So we start with this 4 and represent that with bit 1. So we already covered 4 and 4, so these next 2 bits will be 0. So that's how you get the binary representation of 4. Now for 5, that's like 4, the most significant bit we can use, and the remainder is 1. We have to represent 5, and we represent up to 4. So we cannot put a 1 for 2 because that will be like 4 plus 2, 6. So we'll replace 0, and then you can put a 1. So 4 and 1 are with bit 1, so that's 5. 6 is like 1 for 4, and remaining is 2. We can put a 1 for 0, and that is 6. Is that clear now? And then
Yes, sir.
1, 1, 1. And 8 is going to be 1 for 8, and then 0, 0, 0. So this is what I mean. The number of bits for 8, the integer 8, is 4 bits, and that is same as telling the number of bits needed for half of 8, which is 4, and number of bits needed for 4 is 3 plus 1 more bit. So that's the recurrence here. And for 8 it's for 9 it's 1, 0, 0, 1. So the number of bits for 9 according to this recurrence is the number of bits needed for half of 9. Half of 9 is also 4, and the number of bits needed for 4 is 3 plus 1 more bit, so that's 4. Okay, is that clear now?
Yes, sir.
Okay, alright, any other question?
No.
Okay, alright. So what we need to now look at is how to solve this recurrence relation. So if you notice here, the format of this recurrence relation is different from what we had for the factorial problem. If in the factorial problem, m of n is m of n minus 1 then plus 1. So the key thing to notice is n here in the lower order terms decreases by 1. So we had n minus 1 plus 1, and we are able to reduce it to m of n minus 2 plus 2, then to m of n minus 3 plus 3, and so on. Whereas here you see the lower order terms are going to be like, if it is n, it is n over 2. So it's not like n minus 1 or n minus 2 and so on. So we cannot use this approach of reduction to lower order terms in this to solve this recurrence relation. But we know one approach, which is reducing to lower order terms like linearly like this, to 1, n minus 1, n minus 2, n minus 3, and so on. So we will try to bring this recurrence in that format in which you can apply that approach and then solve this recurrence relation. So that's what we are going to do. Okay. So in order to bring this recurrence relation in that format, what we are going to do is like a substitution approach. So you see here we have a trend that this is the range is doubling, right? So we can write this n as 2 raised to k. K is also an integer greater than or equal to 0. Okay, so if I replace n with 2 raised to k, a of n is a of 2 raised to k, then n over 2 is going to be 2 raised to k divided by 2. So 2 raised to k divided by 2 is a of 2 raised to k minus 1. Then this plus 1 stays as it is, plus 1. And now you see this recurrence is true for n greater than 1. So we need to find the equivalent value of k. So we want to solve for like n greater than 1. So for what value of k, 2 raised to k will be greater than 1. So if k is 0, 2 raised to 0 is going to be 1. So 1 cannot be said as greater than 1, right? So we cannot say 1 is greater than 1. So we have to go for the next value of k, which is 1. So if k is 1, 2 raised to 1 is 2, and that is greater than 1. So that is why you see here I have said this recurrence in terms of k is greater than 0. That means like greater than or equal to 1. Okay. So we can, so these two recurrence relations, a of 2 raised to k equals this one, is equivalent to this relation with the substitution that n equals 2 raised to k. Okay. So for so this is for k greater than 0. So now what about k equal to 0? So k equal to 0 is a of 2 raised to 0, and that is, according to this recurrence, a of 1 equals 0. That's a basic condition for n equal to 1. So 1 can be written as 2 raised to 0, that's what we have here, and that is equal to 0, and this 0 follows from that. So the basic condition that we had earlier, a of 1 equals 0 for n, can now be written in terms of k as a of 2 raised to 0 equals 0. So this is now the recurrence relation in terms of k. And if you notice here, we have that trend of the lower order terms being reducing by 1, at least in the exponent. So this is like a of 2 raised to k equals a of 2 raised to k minus 1. And once we have in that format, we can use the approach that we had for factorial and solve for k first. And that's what we are going to do. So a of 2 raised to k is a of 2 raised to k minus 1 plus 1, and now we try to reduce to lower order terms. So we can now write a of 2 raised to k minus 1. So replace k with k minus 1 in this recurrence relation. So that's going to be a of 2 raised to k minus 1 minus 1, the exponent. So that is a of 2 raised to k minus 2 plus 1. Okay, so replace k with k minus 1 in this recurrence. We can get a of 2 raised to k minus 1 is a of 2 raised to k minus 1 minus 1, that is a of 2 raised to k minus 2 plus this 1. So now substitute for that here, we'll get a of 2 raised to k is a of, this can be replaced with this recurrence that we just came up with. So a of 2 raised to k minus 2 plus 1, and then this plus 1 comes here. So that means it's a of 2 raised to k minus 2 plus 1 is plus 2. So now we can again write a of 2 raised to k minus 2 in a further lower order term by replacing k with k minus 2 in this recurrence. So a of 2 raised to k minus 2 is a of 2 raised to k minus 2 minus 1, that is a of 2 raised to k minus 3 plus 1. Okay, let me make sure I'm starting the recording. Okay. So replace a of 2 raised to k minus 2 as a of 2 raised to k minus 3 plus 1 plus this 2. So that is a of 2 raised to k minus 3 plus 3. So you see a trend now. If it is a of 2 raised to k minus 1 plus 1 for a of 2 raised to k, you can also write it as a of 2 raised to k is a of 2 raised to k minus 2 plus 2 or k minus 3 plus 3. So in general, a of 2 raised to k can be written as a of 2 raised to k minus I plus I. And that's the so in discrete structures you would have seen called proof by induction, and in that course you should have done some reconciliations like this and proved why we can generalize like this. So in this course we are not going to really go through the details of proof by induction, and we are going to just use reduction to lower order terms for few terms like this, k minus 2, k minus 3, and in general you can write it as a of 2 raised to k minus I plus I. So again, like the factorial problem, we need to solve for I and find and see how much we can go lower for the right hand side function here. So according to our basic condition here, we can go all the way to 2 raised to 0. So that means we need to find for what value of I this will be a of 2 raised to 0. So that will be again like writing k minus I equals 0. So that will be like I equals k. A of 2 raised to k minus I is 2 raised to 0. So that's like k minus I is 0, same as I equals k. So we'll substitute I equals k in this recurrence. So that will be a of 2 raised to k is a of 2 raised to k minus k plus I equals k. So that's k. But a of 2 raised to k minus k is 2 raised to 0. A of 2 raised to 0 is 0. So that's why we wanted to reduce it all the way to the basic condition by doing this substitution for I equals k. So that will be like a of 2 raised to 0 is 0 plus k. So 0 plus k is k. So now we got a of 2 raised to k is k. So now we need to replace things back in terms of n. So 2 raised to k is our n. So a of 2 raised to k is same as a of n. On the right hand side we have just k. So if n equals 2 raised to k, we saw a property of logarithm where we can say if n equals 2 raised to k, k is log of n to the base 2. So this is what k is, log of n to the base 2 if n is 2 raised to k. And we can write this as theta notation simply as log n. So as I said before, once you write inside theta notation, we can remove the base and simply say it's log of whatever it is, n or n square. In this case it is just n. So that means a of n is theta of log n. That means the number of additions we need to do to represent an integer n in binary increases as log of that n. So slow growing function, right? So the key thing here is once we get this recurrence in this format, notice that it is n equals a of n over 2. So it's not in the n minus 1 format or n minus any linear thing. It could be n minus 1 or n minus 3, but it's not linear. So it is division. So that's why we have to, whatever is the denominator, we have to use that. So if n equals, in this case 2 is in the denominator, so we write it as 2 raised to k and solve for k first. I have one more recurrence we can solve with the same approach where we have n over 3, and there here we'll do n equals 3 raised to k because 3 is what is in the denominator. We'll do this recurrence quite soon. Before that, any question up to this point, how to solve recurrence relations like this? So there are two formats. One is this one, like factorial problem, and the other is this, but we can transform this to the first format and solve for that. Okay. All right. Any question? All right. Let me save this video and then we'll